sort of the role of topology in band theory in 1 dimension, 2 dimensions, and some generalizations. And so let me just sort of start with the sort of big ideas, which are symmetry and topology. And these are sort of two of the most sort of powerful organizing principles that we have for thinking about physics, thinking about matter. So symmetry, of course, is about what you can do to a system that keeps it the same. Okay, you can translate it, you can rotate it. There are all kinds of symmetries, and those are very powerful things to understand. They give you conceptual simplification, they give you conservation laws, and importantly for what I want to discuss is they allow you a principle for distinguishing phases of matter. Okay, so for instance, the solid phase, the crystalline phase of matter has patterns that look kind of like these. Okay, and by understanding those symmetry patterns, one can understand a lot. So an equally powerful idea, however, is topology. And what topology is about is it's about sort of what stays the same when you continuously deform something. Okay, and so the classic example is the sense in which a sphere is the same as a bowl, or the sense in which a donut is the same as a coffee cup. And again, topology comes up in many contexts in physics, but what I want to focus on is the using topology to distinguish topological phases of matter. Okay, and this is a little bit of an old idea. The role that topology has played in physics has gone on for many decades. But what's a little bit newer, what's been sort of at the root of a lot of current activity has been the interplay between symmetry and topology, and so that's given us a new way of thinking about electronic phases of matter. And so that's what I'd like to introduce you to. Okay, and so where does topology enter into thinking about electronic phases of matter? And where so when you think about topology, you have to think about smoothly deforming things. Okay, and so where that comes in physics is through the idea of adiabatic continuity. Okay, and so if you have an eigenstate, a many-body eigenstate of your system that's separated by an energy gap from all the other eigenstates, then you can imagine very slowly deforming this, changing the Hamiltonian, and the system will follow that ground state adiabatically. Okay, and so if you have eigenstates that are related by this adiabatic continuity, then that gives you a notion of topological equivalence. Okay, and so if you have a quantum phase of matter, a phase of matter that has a ground state and then has excited states that are separated by an energy gap, if you deform the system and you stay in that ground state, then you can say that you're staying in the same phase. Okay, so quantum phases with an energy gap are topologically equivalent if they can be smoothly deformed into one another. Okay. Now, of course, not everything is the same, and that's where all the interest lies. So topologically distinct phases, necessarily you have to go through a quantum phase transition where the energy gap goes to zero. Okay, and so all the interest is in understanding, well, what are the kinds of topological phases that you can have? Can we characterize the topological, can we characterize the phases, and can we characterize the quantum critical points that separate them? Okay, now, in general, this is a really, really hard problem. Okay, and I think even today we don't have a complete characterization of many-body topological electronic phases of matter. Okay, it's a hard problem. But there is a part of that problem that is relatively easy. And that's a problem if you can think about problems where band theory works. Okay, and so basically what band theory does is it takes the many-body problem and turns it into a whole bunch of one-body problems. Okay, and it works provided you can ignore the interactions between particles, so you can just treat one electron at a time. Okay? And in the context of band theory, which of course is a very powerful tool for understanding the electronic structure of materials, in band theory, you think about the single particle energy spectrum, and you have a set of occupied states and a set of empty states, and if they're if the valence band and the conduction band are separated by an energy gap, then you fill those states up. The many-body ground state has an energy gap. Okay, and so now one can think about topologically classifying the single particle Bloch states that one has. And so this is a problem which we do know how to solve. Okay, and so, so I'm going to introduce you to the methods of topologically classifying the single particle states of matter. Okay, this has turned into a very fruitful endeavor. Okay, there are many, many examples of topological band phenomena that occur in real materials that people do experiments on, and so it's a very productive thing. It's not that that in these materials there aren't any electron-electron interactions. Okay, it's just that these are states which are basically adiabatically connected to states where you turn the electron interactions off. Okay, and so examples include the quantum anomalous, the quantum Hall effect or the quantum anomalous Hall effect, Chern insulators, topological insulators, weak topological insulators, and then with more and more symmetries you get more and more phenomena. So there's topological crystalline insulators, there's wild Dirac semimetals. There's many examples of this. And I think several of the speakers this week are going to be talking about different aspects of this in more detail than I will. Okay. Another version of this, which I'll probably talk about a little bit tomorrow, is topological superconductivity. And this is of course, superconductivity involves interactions. But the BCS mean field theory treats it like free fermions, and so one can do the same kind of topological single particle analysis for topological superconductors as well. And this is another area where there's been sort of tantalizing experimental progress. Okay, and so this is another area that's exciting. Now there's a whole frontier out there, okay, of strongly correlated states. Now, of course, we know that such strongly correlated states can happen and that they're interesting because we know about the fractional quantum Hall effect. I think Moti Heiblum is going to be telling us about recent progress in that direction. But there's a question whether we can do for the fractional quantum Hall effect the same thing we did for topological insulators. And so that I think is a frontier and an area where there's been a lot of conceptual progress, a lot of theoretical progress. But I think it's for the younger people in the audience. They're going to be the people who make the connection to real materials. That hasn't happened yet. Okay. Okay. So let me start off just at the very ground zero and talk a little bit about band theory. Okay. So band theory, of course, rests on Bloch's theorem with the translation symmetry of a crystal, which basically tells you that if you have a lattice translation symmetry, then you can choose your eigenstates, single particle eigenstates, to be eigenstates of that translation. Okay, and so that eigenstate of the translation defines the crystal momentum K, and the important thing about the crystal momentum is that it lives in a Brillouin zone, which has the topology of a torus. Okay, so plus pi and minus pi are actually the same point in crystal momentum. Okay, so given this symmetry, one can define a Bloch Hamiltonian, and the beauty of this is this Bloch Hamiltonian only acts within a single unit cell. So basically, you can define the eigenstates of the Bloch Hamiltonian to be periodic with respect to the lattice translation. So that completely, that changes your problem from having the whole system to just having to solve one unit cell. And if you're doing a tight binding model, that means your Hamiltonian is just a, a matrix with however many sites per unit cell you have, okay? So, so that simplifies the problem a lot. And so then one has a mapping between the crystal momentum and your Hamiltonian, okay? Or equivalently, a mapping between the crystal momentum and the energy eigenvalues and the energy eigenvectors, okay? And so that defines a band structure. So a band structure is the collection of all of the block Hamiltonians defined throughout the Brillouin zone. Okay, and if you have a system where you have a set of states that form the valence band and a set of states that form the conduction band, and they're separated by an energy gap, then when you fill those states up with electrons, you'll have an insulator. Okay, so so the question is how do we think about the topological classification of band structures? Okay, and so in order to introduce that, let me introduce the most powerful concept, which is the concept of the Berry phase. So the Berry phase is something that arises whenever you have a Hamiltonian that depends continuously on some set of parameters. Okay? So in the present case, the parameters that we're talking about are the crystal momentum. So we have a block Hamiltonian that depends on K. But it could be any set of any parameters. There could be some knob that you can tune that continuously changes the Hamiltonian. So where the reason that the Berry phase arises is because in quantum mechanics, nobody tells you what the phase of the eigenvector should be. Okay, so there's an intrinsic ambiguity. If I change the phase of the eigenvector, that's just as good an eigenvector as the one you started with. Okay, and you can change the phase in a way where that phase depends on your parameter, depends on momentum. Okay, and it's that intrinsic ambiguity that gives us the Berry phase. And so what it invites us to define, you see what this looks like is it looks like a gauge transformation in ordinary quantum mechanics. In ordinary quantum mechanics, when you do an electromagnetic gauge transformation, that happens along with changing the phase of the wave function. Okay, and but now we're doing it, in the space of these parameters, in momentum space, if you will. And so that invites us to define a version of the vector potential. Okay, and so we call this a connection. And so this quantity behaves like the vector potential in ordinary electromagnetism. If I do a gauge transformation where I change the phase, then this vector potential changes, according to the gradient of that phase. Okay, just like in electromagnetism. Okay, and now in electromagnetism, of course, the vector potential is not gauge invariant. It's not really a physical a quantity that you can measure, but you can measure the flux of the vector potential, which is a gauge invariant, and that's what the Berry phase is. So the Berry phase is the change in the phase going around a closed loop, and that's the loop integral of this Berry connection. Okay, and if you do a gauge transformation, then this does not change. Okay, and so this is something which is physical, and so we want to figure out how to attach physical meaning to this gauge invariant quantity. Okay, so this is the Berry phase, and so one can write it, just like in ordinary electromagnetism, you can write the flux, which is the integral of the vector potential around the loop. You can use Stokes' theorem to write that as the surface integral of the magnetic field. So you can do the same thing. So we can define the curl of this Berry connection to be the Berry curvature, and so then the Berry phase will be equal to this Berry curvature integrated over the surface, a two-dimensional surface in parameter space. Okay. Okay, so this is a general concept, but what it's very useful to do is to have a specific example in mind where you can understand everything, okay? And so Berry introduced this very simple model which sort of captures the essence of what the buried phase is all about. And so this is the simplest Hamiltonian you can imagine. It's just a two-level system. So your Hamiltonian is a 2x2 matrix, okay? So if this was going to be a tight binding model, it would be a tight binding model in which you have two states per unit cell, okay? But it applies more generally. So I have a Hamiltonian, which is a 2x2 matrix, and so of course there's a constant piece you can add, and that doesn't change the eigenvectors at all, okay? So the only pieces that are important, I can write any Hamiltonian as a constant piece plus some combination of the three Pauli matrices. Okay, so that's an arbitrary 2x2 Hermitian matrix, can be written like that. And so I can think of it's just like a spin in a magnetic field. Okay, and so the only thing I have to think about, there's the magnitude of the magnetic field. Of course, that doesn't change the eigenvectors. It's the direction of the magnetic field that chooses the eigenvectors. Okay, and so. So this is a 2x2, two-level system, and so Berry's famous result, okay, which is worth deriving for yourself if you've never seen it before. Okay, everybody has to go through that at least once. Okay, so if you haven't, then this is a good problem to work out, which is the Berry phase. So I can if I imagine taking K through a closed loop, then this vector D will sweep out some solid angle on the sphere. Okay, and so Berry's famous result is that the Berry phase is exactly equal to 1/2 of that solid angle. Okay, and so just as an example of this, so if you have a spin and you rotate it by 360 degrees, so you take it around 360 degrees like that, then the Berry phase is half of the hemisphere, which has solid angle 2 pi, so the Berry phase is pi. Okay? And so that's the minus sign that you pick up when you rotate a spin by 360 degrees. Okay? So that's an example of a Berry phase, but of course the Berry phase is more general than this. Okay, so this is this general concept. So how does the Berry phase show up in thinking about the electronic structure of materials? And so what I want to argue to you is that, excuse me, the Berry phase tells you about the electric polarization. Okay, and so let me remind you about the just classical electric polarization. So you learn this about in freshman E&M. If you have a material that has a dipole moment, then if I have a bunch of dipoles, then on the inside there's no charge. All the charge is compensated. But on the edge, then there's some uncompensated charge, which is like the dipole moment per unit length dotted into the normal. Okay, and so you can have a bound charge or you can have a surface charge. Okay, so there's and so of course the electric polarization is a fundamental quantity for ferroelectric materials, which have an intrinsic electric polarization. And so there's a problem. How do you calculate it using band theory? Okay, and it's not so trivial because in band theory, what you always do, you always write your states in terms of K, and so implicitly what you're doing is you're putting your system on periodic boundary conditions. So you don't have a surface to measure that polarization charge on. Okay, and so how do you extract the polarization from the band structure? Okay, so what I want to try to convince you of is that it's the Berry phase. Okay, and so we start off and we have the block states, which are basically plane waves which go around. They're completely delocalized. So the polarization you think of it's like the dipole moment, but you can't calculate the dipole moment in a state that's completely extended. Okay, but you have lots of extended states. You have an extended state for every crystal momentum, and so I can combine those together to form states that are localized. Okay, and so these states are called Wannier states, and I can just it's like doing a Fourier transform of the block states, and I can define a Wannier state for every lattice vector. Okay, Provided my block states are defined continuously throughout the Brillouin zone, so there's no singularities in how they're defined, then these Wannier states will be, I'm taking the Fourier transform of a smooth function, so they'll be well localized. Okay? And so it makes sense then to compute the dipole moment of one of those Wannier states. Okay? And if you do that, then you can sort of undo the Fourier transform. Okay? So this is the dipole moment of the Wannier state. It's basically its center of charge relative to its where it's centered on. Okay? And if you just plug in the Fourier transform, okay, then what you can see is that you end up with something like this. Okay, so this is another good exercise to do if you haven't seen this before. Okay. So this has the structure, precisely the structure of this Berry connection. So the electric polarization is precisely this Berry phase. Okay. So in one dimension, the Brillouin zone is a circle. Okay. And so what we are doing is we're computing the Berry phase of the block states going around that circle. Okay. So now this is all nice and beautiful, but there's a little bit of a problem with this. Okay, which is that I told you this Berry connection is not gauge invariant. Okay, and actually the loop integral of the Berry connection is not quite gauge invariant either. Okay, and this points us to an important fundamental property that both the electric polarization and the Berry phase share. Okay, which is they're both ambiguous up to an integer. Okay, so and it makes complete sense if you think about the polarization. Okay, so you can ask the question. So if I define the polarization, as it's the dipole moment per unit volume, the way you can measure it is by measuring the charge at the end. Okay, so you can ask the question: well, to what extent does this bulk property, the polarization, determine the charge at the end? Okay. Now you see, I can always take another electron and add it to the end. Okay, so it certainly cannot, so it can only determine the charge modulo the quantum of electric charge. Okay, and so in that sense, this polarization is really only defined mod E. Okay, likewise, the Berry phase, if I do a very small gauge transformation, then since I'm going around in a closed loop, everything cancels and it is gauge invariant. But if I do a gauge transformation where I change the phase in such a way that the phase, when I go around the circle, changes by a multiple of 2 pi, okay, so we call this a large gauge transformation. So it's like I'm putting a vortex inside the circle so that the phase winds by 2 pi. Then if you do that gauge transformation, which is a perfectly good gauge transformation, then the polarization defined as a Berry phase changes by an integer multiple of E as well. Okay, and so these two ambiguities sort of go hand in hand with each other. Okay, and so it should make us happy that both the physical polarization and the Berry phase share this intrinsic ambiguity. Okay, so it all makes sense. Okay, now so you can say, well, the polarization isn't well defined. How can we possibly think about it? Well, that's true, but changes in the polarization are well defined. Okay, so if I start with some system and then I have some knob that I tune that changes the system, then I can compare the polarization at the beginning and the end. And if I demand that I don't add any electrons to the end, in that process, then that should be a perfectly well-defined quantity. Okay, and so if I introduce a parameter lambda, and I change my band structure, slowly, adiabatically, Then I can compute the difference. So now I can think of the band structure now as a function of lambda and k. Okay? And so if I compute the change in the polarization, that's going to be the difference of the Berry phases along these two circles. Okay? And now, you see, notice that the loop that I'm integrating over. So actually, let me go back. So when I talk about this circle here, this loop is a funny kind of loop because it is a loop that is not the boundary of an interior. There's no inside of this circle, whereas here now, these two circles are sort of at the ends of this cylinder. They do have an interior. Okay? And so I can use Stokes' theorem now to write, this change in the polarization as the gauge invariant integral of the Berry curvature over this two-dimensional surface now. Okay, and so everything is well-defined and gauge invariant. Okay. So this is the electric polarization. Now again, this is all general. It's very useful to have a specific model in mind in order to be able to think about these ideas. And so there's a very nice one, which is called the Su-Schrieffer-Heeger model. And so the Su-Schrieffer-Heeger model was introduced as a model for polyacetylene, which is a conducting polymer. It's basically a chain of carbon and hydrogen atoms. And so polyacetylene is an insulator, but it's a kind of interesting insulator. So the reason it is an insulator, so you can basically think it's basically a half-filled chain of atoms, okay, with basically one electron per unit cell, okay. It's a half-filled band, okay. And so what polyacetylene would like to do, though, is it would like to dimerize and form strong and weak bonds. And if it does that, then it does this because of what's called the Peierls instability. If you dimerize, then you open up an energy gap. And since you're half filled, you lower the energy of all of the occupied states. Okay? And so that's why polyacetylene is an insulator. Okay? But it's interesting insulator because you can do it in two ways. Okay? You can have the dimerization pattern be strong, weak, or you can have the dimerization pattern be weak, strong, weak. Weak, strong. Okay? So what I would like to argue to you is that actually these two patterns are in a sense topologically distinct. Okay, let's think about the electric polarization. So I can write down a simple tight binding model of this. Okay, where I have strong bonds and weak bonds, which are connecting, the A and the B sublattice. I have two. So my unit cell is two atoms. So my Hamiltonian is going to be a 2x2 matrix, and so I should be able to write it as a D vector dotted into a Pauli matrix, where the two states of my two-level system are the A sublattice and the B sublattice. Okay, so clearly the Hamiltonian only connects the A sublattice to the B sublattice. There's no same sublattice hopping, so the Z component, the diagonal component of the D vector, is going to be 0, and it only involves the x and y, and it's not too hard to work out that this is what it is. Okay, and so it's interesting to think about the electric polarization in this case. Okay, let's compute the Berry phase of this quantity, and it depends on whether this delta t is positive or negative. If delta t is positive, then you can see that dx never gets to 0. Okay, and so if I sweep out in the sphere, so of course it's always going to be on the equator, right? Because dz is equal to 0, so I can draw it in the xy plane. This d vector, as I sweep out going from minus pi to pi, this d vector is going to go around this loop here. And so if I think about the area that I'm sweeping out, the d vector is sort of going like this, and so it's sweeping out 0 area. The polarization is 0. Okay, and so in this A phase, the polarization is 0. In the B phase, where delta t is negative, then you can see that, dx can change sign, okay, because this is bigger than this, okay? And so that looks like this. And so in that case, if I follow the d vector around, it rotates by 2 pi, okay? And so that gives us the pi Berry phase, okay? So in the B phase, there's a Berry phase of pi, there's a polarization of E over 2. And it kind of makes sense that to get from the A phase to the B phase, it's like you're moving all the electrons over by 1/2 of a unit cell. Okay, and that gives a polarization of E over 2. Okay. Now, so I'd like to argue to you that the A phase and the B phase are topologically different phases in the sense of adiabatically continuity. Because of course, in order to get from the A phase to the B phase, this dimerization has to go through 0. And when the dimerization is 0, then the energy gap has gone to 0. So that's your quantum phase transition. Okay. Now, it's a little bit more subtle than that, though, because actually, what's to keep you from adding something where I get a z component to the d vector? You see, what these two. The reason these two are different is kind of they have different winding numbers around the origin. But if I can turn on dz and go over the top, then maybe I could get from this to this without closing the energy gap. Okay, so there has to be something else to the argument. Okay, and that's symmetry. Okay, so provided there is some symmetry that requires that dz is equal to 0, then the states with positive and negative dimerizations are distinguished by an integer winding number. Okay, without some extra symmetry, all one-dimensional insulators are the same. Okay, so there's no topology in one dimension unless you have some extra symmetry. Okay, and so let's just think a little bit about what the symmetries of this Su-Schrieffer-Heeger model are. There are actually 2 of them, and they're both interesting. Okay, so the first one is what is sometimes called chiral symmetry, or particle hole symmetry. Okay, and this symmetry is a artificial symmetry of the Su-Schrieffer-Heeger model. It's not a real symmetry of polyacetylene. It's just a symmetry of the model. But it's kind of a nice symmetry. And what it is so, and again, and it's a kind of funny symmetry. Usually when you have a symmetry, you have an operator that commutes with the Hamiltonian. Well, this is a symmetry where the operator anti-commutes with the Hamiltonian. Okay? And it's obvious, since the Hamiltonian doesn't involve sigma z, since dz is equal to 0, then the Hamiltonian only involves sigma x, and there's no constant piece either. It only involves sigma x and sigma y. So then it anti-commutes with sigma z. Okay? And when you have an operator that anti-commutes with your Hamiltonian, then you are guaranteed to have a particle hole symmetric spectrum. Okay? Because so the reason that you have this in the polyacetylene is because we have a bipartite lattice, A and B sublattice, and the only terms in the Hamiltonian are terms that connect the A to the B sublattice. Okay? And so what I can do is I can do a gauge transformation where I change the sign of all of the electron operators on the B sublattice, and then that will take H to minus H. Okay? So it's this bipartite lattice with only opposite sublattice terms that's responsible for this chiral symmetry in the polyacetylene model. Okay, and that means that dz is equal to 0. But importantly, what it gives you is it gives you a particle hole symmetric spectrum. Because if I have an eigenstate that has some energy E, I can construct another eigenstate which is sigma z acting on that state. Okay, so then if I apply the Hamiltonian to that, then since the Hamiltonian anti-commutes with sigma z, I can pass the Hamiltonian through, and then that gives me a and then it's an eigenstate, so I have minus E times that state. So that tells us that this operator, that this state sigma z acting on the state at energy E is an eigenstate with energy minus E. So that tells us that the eigenstates come in positive E minus E pairs. Okay, and so it has a symmetric spectrum. And indeed, if you look at this spectrum, it is symmetric. Okay. Okay, and now this is an artificial symmetry in poly, so there's nothing to keep you from having second neighbor hopping in real polyacetylene. Okay, and there's no zero in real polyacetylene either. There's no energy that has the right to be called zero. Okay, but nonetheless, this is actually a very useful symmetry to think about. And later on, we're going to be seeing some situations where this kind of chiral symmetry or particle hole symmetry is a real intrinsic property. Okay, so when we get to topological superconductivity, for example, the particle hole symmetry will be real. Okay. Okay, but polyacetylene does have another symmetry though, which is real. Okay, and that's reflection symmetry. So if you look at this, I can reflect about the middle of a bond, and that looks the same. Okay, so so that also is a symmetry of the Hamiltonian, but this is a symmetry that relates h of k to h of minus k. And now actually, that doesn't forbid second neighbor hopping, so actually the dz can be non-zero, but it does give us a constraint, and what that boils down to is that the two phases, the two dimerization patterns, are still topologically distinct. Okay, and in fact, they're separated by they're distinguished by a Z2 invariant, not an integer winding number anymore. Okay, and basically the reason for that is you can think that the polarization, if you have reflection symmetry, then the polarization has to be equal to minus itself, because if I reflect, then the polarization changes sign. So the polarization can be zero. Zero is equal to minus zero. Okay. But the polarization can also be E over 2, because remember, the polarization is only defined modulo an integer anyway. Okay, so E over 2 and minus E over 2 are the same. Okay, so E over 2 is allowed as well. But those are the only two values. So, so the polarization can be 0 or E over 2, and that kind of defines a Z2 topological invariant. Okay, all right. So, okay. So let me tell you about the most important consequence of all of this. About the fact that you have these two topological classes for this one-dimensional insulator, and so this is the idea of topological boundary modes. And in general, when you have the boundary between topologically distinct insulators, there are necessarily topological boundary modes that live on the interface between them. Okay, and so the simplest context for seeing this is in this Su-Schrieffer-Heeger model, where if I have a domain wall, then I have a region where I have the dimerization pattern in this way on one side, and I have it the other way on the other side, and it's completely obvious that there's going to be a zero energy state if you consider the most extreme limit, which is the limit where the strong bonds are really strong and the weak bonds are equal to 0. Okay? Because in that case, then each of the strong bonds, you're going to have two states which are strongly coupled. They're just going to split, and you have a big gap. Okay? And so everything's split on this side, everything's split on this side, but there's this sort of leftover site which isn't coupled to anything, and that's going to stay at 0. So that's your 0 mode. Okay? Now, the interesting thing, though, is, well, what happens if I turn up, that's an extreme limit. But let's turn up the weak bonds now so that they're not 0 anymore. So you can ask the question, well, what would happen if I smoothly turn up the weak bond? Okay? Now, so let's believe that we have particle hole symmetry. Okay? So I have a reflection symmetric spectrum. Okay, that means every state at positive energy has a partner at negative energy. Okay? Now, this zero mode here, it's still reflection symmetric, but this is special because this zero mode is its own partner. Okay? So you can ask, well, what could happen to that if I turn up the weak bonds? Well, nothing can happen to it, right? Because if it tried to move away from zero, it would have to have a partner that appears out of nowhere. Okay, and that can't happen smoothly. Okay? So this zero mode has to stay at zero, as you turn up this weak bond. And in fact, it'll stay there as you turn it up until the weak bond is completely equal to the strong bond, in which case the bulk gap goes to zero. Okay? So this zero mode is topologically protected. You can't get rid of it. Okay? At least if you have this particle hole symmetry. Okay? Now, so actually this phenomenon was actually sort of discovered by the field theorists who are looking at it from the opposite limit. Okay? So if you think about the sort of the structure of this model sort of close to the Fermi energy, imagine the mass is small. You can sort of look at low energy sort of around at the low energy states here. And that has the structure of a one-dimensional Dirac Hamiltonian, okay, where the dimerization gives you this mass term, okay, and this is coming from the finite Fermi velocity of the states that are crossing at pi, okay, and so what Jakiv and Rebbe realized is that if you have this one-dimensional Dirac Hamiltonian and the mass changes sign at a domain wall, okay, then you have a topologically boundary mode there. Okay, and again, it's really the same thing. So this Hamiltonian also has the particle hole symmetry, has the chiral symmetry. So and again, it's guaranteed to have a reflection symmetric spectrum. And so if you have this domain wall where the mass changes sign, then what they proved is that there is an exact eigenstate at zero energy that's localized on this boundary. Okay? And this exact eigenstate that they found, if you have not been through this calculation, this is another assignment. And this is a very satisfying calculation to do because once you've done it, you realize it's really easy. Okay? Which is to show that the exact, that this Hamiltonian has an exact zero energy eigenstate with this wave function. Okay? And it's really easy. So all you have to do is solve h psi is equal to 0, and then you have a simple one-dimensional first-order differential equation that it's easy to integrate. Okay? So, so this is the Jakiv-Rebbe problem. Okay? So, okay. Now I want to make one comment about this. So all of this discussion, I've been talking about the single particle eigenstates. Okay, and so thinking about the one-body eigenstates, I have a one-body Hamiltonian that that has a gap, that has an energy gap, and then on this boundary, then I have this zero energy eigenstate. Okay. Now, of course, real polyacetylene, what you're doing is you're filling up all the negative energy states with electrons, and then you have a many-body ground state, which is all of those filled states. Okay, and so you can ask the question, and of course that you can then turn on some interactions, and it kind of stays the same. Okay, so you can ask the question, well, what happens at this domain wall when you do that? And something very interesting happens, which is that so if I fill up all the negative energy states, okay, then you have to ask, well, I can either put an electron in the zero mode or not, okay? But because of the particle hole symmetric spectrum, if you turn the spectrum upside down, it looks the same. Then you know that the total charge, has to go to minus itself. Okay, and so that means whether you have this empty or occupied, it's either going to be plus E over 2 or minus E over 2 on this domain wall. Okay? So this domain wall between the A and the B, if you were to ask what is the charge at that domain wall, it's precisely E over 2. Okay? And so what that means is, putting this, changing the topological phase is sort of a way of splitting an electron in half. Okay? So you can imagine you start in the A phase, and I add an electron, and then I can nucleate a little B phase, and two domain walls move away, and that charge sort of splits in half. Okay? And so this is something that topological phases can do, is they can take things which ordinarily are indivisible. Okay? An electron can't cut an electron in half. Okay? But here you can, okay, because you can put it on the boundary between two topological phases. Okay, and and let me just say one other thing, which is once you turn on interactions in polyacetylene, it no longer makes sense to talk about a zero mode. Okay, the zero mode is that's only a zero energy eigenstate of the single particle. That only makes sense if you have non-interacting fermions. Okay, but the charge here, that's well defined in an interacting system, and in fact, that charge survives in an interacting system. Okay, as long as you have the inversion symmetry that make the A and B phase differ in their electric polarization, then actually this E over 2 is just the divergence of P. Okay, the divergence of the polarization. All right. Okay. I think what do I have next? Yeah, maybe this is a good. Why don't we take a 5-minute break, and then I'll come back at 10:05. How's that sound? Okay. Good. Yeah, absolutely.
I've always learned that the chiral symmetry and the particle symmetry are two distinct symmetries.
Yeah.
You talk about them as if they're the same.
Well, yeah. So there are two different kinds of symmetries that involve a reflection E to minus E, and one of them involves complex conjugation, and the other does not. Okay, and so perhaps what you were referring to is particle hole symmetry as the one that involves complex conjugation. Okay, that's the symmetry that is, for instance, the symmetry of a Bogoliubov-de Gennes Hamiltonian in a superconductor, whereas the chiral symmetry that we're talking about does not involve complex conjugation. So it depends whether it's a unitary or an anti-unitary symmetry. Yeah. Good. And any other questions? And by all means, I like getting questions. So even while I'm talking, feel free to raise your hand or interrupt or whatever. Okay. Okay. Good. So let's come back in 5 minutes then.
Ask questions because speakers tend to speed up and you need to slow them down and you need to understand stuff. So please interrupt.
Hey, Steve. Hey, good to see you. Okay, welcome back, everyone. So the next thing that I want to do, so I made this point that in one dimension, when you don't have any extra symmetries, then every insulator is the same as every other insulator. Okay, there's no topology in one dimension. But I want to tell you about a situation in which actually there is topology in one dimension if I allow for adiabatic changes. And so this is the idea of the Thouless charge pump. Okay, and so what I want to imagine is I have a one-dimensional system. There's no symmetries, but I have some knob that I can tune that changes the Hamiltonian as a function of time, say, and I can do it slowly. And so I want to imagine a periodic cycle where I turn my crank through a circle. So after a period capital T, my Hamiltonian comes back to the Hamiltonian that I started with at t equals 0. So I have a periodic cycle. I can think of it as like a crank that I'm turning. Okay, and so I want to argue that something interesting can happen. And that, if I think about this Su-Schrieffer-Heeger model, I can think it's like I have a periodic potential, and the electrons are sort of locked in that periodic potential. Well, if I have a knob that slides that periodic potential over by one space, and I can do that smoothly, Okay? After I've gone through one cycle, the Hamiltonians came back to the same Hamiltonian that I started with. Okay? But the electrons have all moved over by one space. Okay? And so what that means is that an electron has moved from one end to the other end. Okay? And I'd like to argue that that signifies a change in the electric polarization by E. Okay? Now remember, E and 0 are the same, right? Because the electric polarization is only defined mod E. But this pumping cycle is a way of getting the electric polarization to change by E. Okay? And I've come back to where I started at the end. Okay? So I can think of this that, so again, my electric polarization, I can think of it, it's the Berry phase. And if I do that, it changes by, if I go through this cycle n times, I get n times E. And I can interpret that as the change in this Berry phase, comparing t at capital T and t at 0. Okay? And if I think of my electronic states as a function of k and this adiabatic parameter t, which, then it will be equal to the Berry curvature. I can use Stokes' theorem to write this integral in terms of a surface integral over the interior of this loop. Okay? And the important thing here, though, is that my Hamiltonian, when I started off at 0, the Hamiltonian at t is the same. Okay? So it's like I've come back to where I started. So I told, so we know that plus pi and minus pi, they're the same point. So k is really defined on a circle. Okay? Well, in this periodic Hamiltonian, t is defined on a circle too. So this region here is really like a torus. Okay? And so what I'm doing is I am integrating the Berry curvature over this entire torus. And what I know is that, since the polarization, since I came back to where I started, the polarization can only change by an integer, because the polarization has to be equal to itself mod E. Okay? So that tells us that this integral of the Berry curvature has to be an integer. Okay? And that integer is a famous integer. It's called the Chern number. Okay? And so if you integrate the Berry curvature over this closed surface, okay, the entire space of K in lambda, okay, and it's a closed surface, doesn't have any boundary, then that is guaranteed to be an integer, provided you define it with the appropriate factor of 2 pi. Okay? And so that's the Chern number. Okay? And so this gives us a way of topologically classifying a system in one dimension with an extra parameter. Okay? You need to have 2 parameters, and you have a Berry curvature as a function of 2 parameters. So again, it's useful to think in terms of this, this 2-band model. Okay? Remember the 2-band model where the Berry phase is half the solid angle that gets swept out. So if you have that 2-band model where now I can think I have this d vector, so my Hamiltonian is defined now as a function of k and t, and so now I have this d vector which is defined as a function of 2 parameters k and d. So I can think of this band structure then as a mapping from the torus, which is the space of k and t, to a sphere, which is the the unit vector d hat. Okay? And so what the Chern number is in that mapping is it's the number of times the torus sort of wraps around the sphere. Okay? Everything could go to one point, in which case it would be 0. Or I can have it go all the way around the sphere, any integer number of times. Okay, and you can write that as an integral. So if you just in every solid angle, you can write down what the in every element of every area element of the torus, you can write down the solid angle on the sphere that gets swept out. That's going to depend on, derivatives of d hat. And you add them all up, and this gives you a formula for the, for the number of times that, that d hat wraps around the sphere. Okay, and so in the two-band model, the Chern number is just the sort of winding number of this d vector on the sphere. Okay, all right. Now, so once we do it like this, then this sort of invites us to think about two-dimensional band structures. Okay, and so this is what the TKNN invariant is after Thouless, Komodo, Denise, and Nightingale. And so if we have a two-dimensional band structure, then we have two parameters as well. We have kx and ky. Okay, and so I can define my Berry connection. It's going to be a two-dimensional vector now in momentum space. And again, I can think about the sort of Berry phase on the Brillouin zone, the two-dimensional Brillouin zone. And so, if I think about the Berry phase going along here and the Berry phase going along here, since the Berry phase is only, defined up to an integer, then these have to be equal to each other modulo an integer. Okay, but I could equally well integrate over the, I could use, Stokes' theorem to integrate over the boundary, so that's got to be equal to the integral of f, and that tells us that the integral of f has to be equal to an integer. Okay, and so if I have a two-dimensional band structure with an energy gap, then those two-dimensional band structures are classified topologically by an integer. Okay, the integer Chern number of the occupied valence band. Okay, and so what does this mean? So the physical meaning of this integer is the Hall conductivity. Okay, and so this goes back to a very famous argument due to Bob Laughlin, which is the following. So let's imagine that you have a Hall conductivity. Okay, this is the quantized Hall conductivity, which is sigma xy. And let's suppose that that you have a system that has an excitation gap. Okay, so what that means is that if there's an excitation gap, then I can adiabatically thread magnetic flux through a cylinder. So I'm going to put it on a cylinder, and I can adiabatically thread magnetic flux. Okay. Now, if I do this adiabatically threading the magnetic flux, I have a dB dt, right? Because I'm turning up the magnetic field, the magnetic flux, and so Faraday's law tells us that when you have a d phi dt, you have an EMF. Okay, and that EMF is going around the loop, and if you have a Hall conductivity, then there is going to be a current I. Well, there's going to be a current J, which is sigma xy times E. Okay, and so and that basically tells you that in the process of turning this flux up by one flux quantum, you have transferred, if you have a Hall conductivity of n, you've transferred n electrons. Okay, and so basically what this Thouless, what this Laughlin argument does on treating the quantum Hall effect on a cylinder is it turns it into a Thouless charge pump. Okay, so think about this cylinder as a one-dimensional system. Okay, where the flux going through it is my parameter that I'm tuning. Okay, so Thouless tells us that when I come back to where I started, and when I thread a flux quantum through, I've come back to where I started. The spectrum is exactly the same. Okay, so what Thouless tells us is that the polarization has to change by an integer, and that integer is equal to the Chern number. Okay, And what Laughlin's argument tells us is that the amount of charge that gets transferred is given by the Hall conductivity. Okay? And so put those two together, that tells us that the Hall conductivity is the Chern number. Okay? And so that's the essence of this idea. Okay? And so so two-dimensional band structures are characterized by an integer, and that integer tells us the quantized Hall conductivity. Okay? Now, there's another calculation you can do, and this is actually the one that Thouless did first, which is you can just compute the Hall conductivity in this two-dimensional band structure using linear response theory, okay, using the Kubo formula. Okay? And what you find when you do that is you find that the Hall conductivity is given by exactly the same formula as the integral of the Berry curvature. Okay? And so that's another calculation which is worthwhile to go through. Okay. All right. Okay. So, okay. So how can you get a non-trivial Chern number? So of course, one way to do it is the quantum Hall effect, okay? Which of course, you have a two-dimensional electron gas and a magnetic field, and that gives you Landau levels, and so that gives you this excitation gap. And so then the Chern number is just going to be equal to the number of filled Landau levels, okay? But by now we have other ways of doing this as well, and of course this goes back to Haldane, who wrote down a very simple model on a honeycomb lattice. As long as you break time reversal symmetry, then it's in principle possible to have a non-zero Chern number. Okay, and so Haldane wrote down a very simple way of accomplishing that, basically starting with graphene and turning on a second neighbor hopping term that breaks time reversal symmetry. Okay, and he was able to see that you can get a filled Chern band. Okay, now there's a very useful way of sort of organizing your thoughts about this, which is to think about, if you're trying to get a non-zero Chern number, you can think, well, let's suppose I start with a trivial insulator. What do I have to do in order to get to a non-trivial one? And so what you need to do is you need to go through a transition where the conduction band and the valence band touch each other, and then the gap opens up again, and maybe they can open up on the other side. Okay? And so thinking about these band inversions is a very powerful way of thinking about topological insulators in general. Okay? So it's sort of, how do you get to it? Okay? You get from a trivial to a topological insulator by doing some kind of band inversion. Okay? And so I want to just talk about this a little. There's a very simple model that you can write down for this. Okay? So what you can basically do is, so I can write down a lattice model, which is to just imagine that I have, say on a square lattice, there's a tight binding model on a square lattice, and imagine that I have S states and then states with a sort of, again, two bands, okay? So I have an S state and a P state. And I'm going to pick the P state that has, M equals 1, so it's like P plus IP. So if I have those two symmetries, then I can just write down a lattice model. So the hopping, from S to S or from P to P is just going to be the usual hopping term. And then there's going to be a hopping term which connects the S and the P states. And that necessarily is going to have a phase which, depending on what direction you're going, is going to be 1i minus 1 or minus I. Okay, and so that's going to give us sine kx instead of cosine kx with the Pauli matrices tau x and tau y, where tau z is the tells you which band you're in. Okay, and so if you just write down this model, it's very simple. Then you can do exactly the same kind of analysis that I did for the Su-Schrieffer-Heeger model. Okay, and so what you can see is that if the S state and the P state are very far away from each other, then basically you get just a trivial insulator, as you should. Okay, and if I think in terms of the D vector, Okay, so I can do the same analysis of the d vector. So if I think of this Hamiltonian as a vector dotted into the Pauli matrix, okay, then when this term dominates, if delta ESP is very large, then basically it's always going to be pointing pretty much in the z direction. And so as I, so it's not going to wrap around the sphere at all. Okay, so it's always going to be pointing towards the North Pole. Okay, whereas if I make the band inversions smaller so that these two bands start to overlap, okay, then what you can see is that this d vector is going to wrap around the sphere. Okay, and so this will be a Chern insulator. Okay, now it was important that I had this P plus IP term, which gave me these, tau x times sine kx and tau y times sine ky. That was important so that I, sort of open up a gap everywhere here. Okay. But in any case, so this is a Chern number one. Now, so this is a nice lattice model. There's an even nicer model that you can write at low energy, which is, you can imagine, let's suppose that you start very close to where these two bands are just about to touch, okay, and then do a low energy theory right around the touching point, okay, and so then you can sort of expand for small k, okay, and if you do that, then you get a Hamiltonian which is going to be the tau x and tau y terms are going to be kx times tau x and ky times tau y, okay. And then for the tau z term, there's going to be the mass term, which comes from this and from the zero values of the cosine. That's basically the mass term is basically telling you where this energy is relative to this one, okay, whether they've crossed or not. And then you also you need to keep a k squared term here, and this k squared is important. Okay, and so in this model, again, you can analyze it like this, and you can see that when m is positive, then it's going to look like this. Now, it's important that I kept this k squared term so that when k is large, I know that the tau z term becomes positive. Okay, and so it's this k squared term that allows this theory to know which side is the topological side and which side is the trivial side. Okay, so positive m is the trivial insulator, negative m is the inverted case. Okay, and so this model, again, makes it look very nice. This looks like a 2 plus 1 dimensional Dirac Hamiltonian, okay, with this mass term. Okay, and so once you have this, then it's a simple model to see. So again, the most important consequence of these topological phases is what happens on the boundary. Okay, and so once we have this, then it's easy to see that on the boundary, where the mass changes sign, okay, where I go from a Chern insulator to a trivial insulator, then there has to be some topologically protected mode on the edge. Okay, and so let's think about what that will be. So so I can think about it. Let's think about it in terms of this Dirac Hamiltonian. Of course, these edge states are completely general. So actually, it's the sort of simple baby picture of these edge states is that when you have the integer quantum Hall state, I can think of that as cyclotron motion. The electrons are going around in circles. Okay. If I have a wall where the with insulator with vacuum on the other side, then the electrons can bounce off the wall, and that gives you this skipping motion, which only goes in one direction. Okay. Now, so let's think of it though. Let's suppose that we have a transition between a Chern insulator and a trivial insulator. So the Chern insulator has an inverted mass, negative m0, and the trivial insulator has a positive mass. Okay. So then what happens is this mass changes sign, and so now we have exactly the same Jakiv-Rebbe problem that I showed you before. Okay. So in fact, and it's, solving it is just as easy. Okay. So because so what I have now, so what I need to do is I need to write this Dirac Hamiltonian in real space. So I can replace kx by minus I d by dx. Okay. Now ky, if y is this direction, I can choose my states. I still have translation symmetry in the y direction, so I can choose my states to be eigenstates of ky. So I'll leave this ky here. Okay. And then, as a function of x, what I want to imagine is that the mass changes sign. Okay. And so for each value of ky, I have exactly the same Jakob-Rebbe problem that I solved you for in the Su-Schrieffer-Heeger model. Okay, so for each value of ky, I have a one-dimensional problem that has this exact, and of course the eigenstates are plane waves in the y direction, and in the x direction I have the exact same Jakob-Rebbe solution that gives me a bound state, and this bound state is going to be an eigenstate of sigma y with a +1 eigenvalue. Okay, and so that means that the energy of this is just going to be Vf times ky. Okay, and so that means that for every value of ky, I have a zero mode, but that zero mode has a dispersion which is linear. Okay, and so this is, and these states are the propagating edge states. So the velocity of a state is really, it's the group velocity. Okay, it's dE dk. And so these states have a positive group velocity. They're propagating in the plus y direction. Okay, and so these states are remarkable things. Okay, so we call them chiral edge states, so they're quite remarkable. Because it's sort of like a one-way street for the electrons. Okay, they only, if you're an electron in this, the only thing you can do is go forward. Okay, and again, so you can think that having the non-zero Chern number in the quantum Hall state guarantees that on the boundary you have some band of states that connects the conduction band to the valence band. Okay, and so and now of course the details of what happens in this edge state could change. Okay, so for instance, there's no rule against it coming up and then coming down and then going up again. Okay, that could happen. Okay, but there always has to be one state which goes from the bottom to the top. Okay, and that's what's guaranteed. And so in a sense, so this sort of follows from a deep principle, which is this bulk boundary correspondence, which is the number of these chiral edge modes, the number of modes that go from the bottom to the top, okay, is equal to the change in the Chern number across the boundary. Okay, and so that's what happens. We have this one-way propagation, and this means that if you put in an electron over here, with 100% certainty it's going to come out here. And it's this fact that sort of underlies the phenomenally precise quantization of the Hall conductivity that's measured in the quantum Hall effect. Okay, the Hall conductivity is something you can measure to 1 part in a billion. Okay, and it's coming because of this perfect transmission. And so one thing that's perfect about it is that it's insensitive to messing it up. Okay, so if you make this edge dirty, okay, now of course if you make it dirty, we don't have momentum conservation anymore. Okay, but you still have the perfect transmission. So because imagine you may have a dirty region here. Okay, you send in an electron. What could possibly happen to it? It can't come. You can't turn around because there's no states for it to turn around into. The only thing it can do is keep going and come out the other side. Okay, and so what that means is that that these edge states are insensitive to disorder. Okay, and they're impossible to localize. Okay, in the history of this, before the quantum Hall effect, it was believed that any one-dimensional system that you could have, if you made it dirty, would become Anderson localized. Okay, and so these chiral edge states evade that because it's impossible to localize them. Okay, and so that's one of the sort of beautiful things about them. Okay, now another thing about these chiral edge states is that they are impossible to have by themselves. Okay, so there's a so let's suppose you just had a perfectly one-dimensional system. Okay, so then there's a doubling theorem that says that the chiral Dirac fermions have to go in pairs, and one way you can say the doubling theorem is what goes up must come down. Okay, because think of this picture. Okay, so if I have a purely isolated one-dimensional system, then I don't have a bulk conduction band and valence band anymore. Okay, but I have to be able to draw my energy as a function of k, and if it goes up, then it has to meet itself, so it has to come down again. Okay, so these chiral Dirac fermions must come in left and right moving pairs. Okay, and so that's the content of the doubling theorem, at least from the point of view of single particle quantum mechanics. Okay. All right. Okay. Now, I have this picture of this sort of thinking about the single particle eigenstates that arise in these edge states. Now, of course, again, I'm going to say this point again and again, which is that in a real system, what you're doing is you're filling all of the negative energy states with electrons, and then you have a many-body ground state. Okay, and so it's useful to think about that, because then maybe to that many-body ground state you're going to add some interactions, and you can ask whether that's important or not. And so I want to just give a few words about the sort of many-body spectrum of this chiral edge state. Okay, and so again, so we can call this a chiral Fermi liquid. So a Fermi liquid, of course, is an interacting electron gas, which basically behaves like non-interacting electrons. Okay, that's the content of Fermi liquid theory. So here what we have is a chiral Fermi liquid, and so this is so one can come up with a very precise description of the low energy excitation spectrum, many-body excitation spectrum of this system. Okay, and it's described by a very simple theory, which is a free Dirac fermion conformal field theory, which is that's just fancy words for a Hamiltonian that looks like this. Okay, and so this is just a Hamiltonian where the dispersion of my electrons is linear in k. Okay, so in that case, I can think about, well, what are the so then I have my states are my single particle states are linear in k. And then my ground state is I fill up all of the states up to the Fermi energy. Okay, so that's my ground state. And so then I can think, well, what are the low energy excitations about this ground state? And so you can see that so you can do two things. You can either add electrons, so you have more electrons, or you can construct neutral excitations, which are basically making particle hole pairs. Okay. And so the interesting thing about the neutral excitations is that if I make a particle hole pair with momentum q, okay, then its energy is exactly v times q. Okay, and so so the dispersion for neutral excitations is linear in q. Kind of looks just like a sound mode. Okay, like an acoustic phonon. Okay, of course, it's only the acoustic phonons going in one direction. Okay, but in fact, one can formulate a theory, even for non-interacting electrons, one could formulate a theory of these low energy, excitations. They behave just like, so sound modes, if you're going to quantize those, each sound mode is like a harmonic oscillator, right? And then you quantize the harmonic oscillators and you have phonons, okay? You can do exactly the same thing here, which is you can write the excited states in terms of some phonon modes. Okay. And then likewise, one can think about, well, I could add, if I start in the ground state, I could sort of get to the ground state. I can add an electron into the ground state with n plus 1 electrons. And so then, if I change the number of electrons, I can think of what the ground state energy is a function of that. Okay. So these two Hamiltonians together form another way of describing the same system, the same non-interacting system. Okay, and so this is what's called bosonization. Okay, and I'm not going to get into too much detail about bosonization, but I just wanted to make this point that even for this simple non-interacting free fermion edge state, there's another way of describing it, where the excitations are sort of like phonon modes. Okay, and this is actually a much more powerful description of the edge state. This is something which one can export to interacting systems. It's something one can export to the fractional quantum Hall effect, and so this is a sort of a powerful beginning for discussion of those phenomena. Okay. Now, irrespective of this, so even when you have interactions, one can think about this, and this still remains true, and it remains that one has a quantized response. Okay, so one has a quantized electrical conductance. So in terms of free fermions, we think of the electrical conductance as being like the transmission of the free fermions. And since these chiral edge states have perfect transmission, then that gives us a perfect E squared over H conductance. One can also think about the quantized electron response in terms of these, many-body formulation. But in either effect, this quantized conductance is something which is robust. And what this quantized electrical conductance reflects actually is it reflects the fact that that these chiral edge states are impossible by themselves. Okay, and so it actually follows from what is called the chiral anomaly. Okay, which is related to the fact that in the presence of an electric field, the edge charge is not conserved. Okay, so that's another reason why you can't have these things by themselves. You see, the reason the edge charge is not conserved is, imagine you have your one-dimensional edge, and you apply an electric field along the edge. Well, what's going to happen is that there's going to be a Hall current that flows in, and the charge on the edge is going to increase. Okay, now of course that current came from the other edge. Okay, so charge is really conserved. But if I had this chiral edge just by itself, then charge would not be conserved. Okay, and so that's the content of the chiral anomaly, and that's intimately related to this quantized Hall conductance. Okay, now there's another a quantized response that you can have as well, and this is something because of Modi Heiblum's recent experiments has become much more interesting than it used to be. And this is a quantized thermal Hall conductance. And so the idea here is that if you have your edge and you raise the temperature, then heat flows along the edge. Okay, and so this is something you can imagine calculating. There are actually two calculations you can do. You can do it for free fermions. Okay, and for free fermions, then changing the temperature just changes the population of the states, and then you can calculate the flow of energy. Okay, that's a straightforward. You just have an integral to do. There's another calculation you can do, which is you can do free bosons. Okay, these phonons, and when you do that, then the temperature tells you the population of the bosons, and that gives you a different integral to do. Okay, but those two integrals turned out to be exactly equal to each other, and that the fact that they're equal is related to the fact that this bosonized representation is an exact representation of the Hilbert space of both problems. Okay, so in either event, what you get is you get a quantized thermal conductance, so the heat flow is proportional to T times these times Boltzmann constant squared over h bar with this pi squared over 3 that comes in when you do the integral, okay, times this number c, which for free fermions is equal to 1, okay? And this has a fancy name. It's called the chiral central charge, okay? And so this C is then something which in principle is just as quantized a number as the Hall conductivity, the integer in the Hall conductivity is in the quantum Hall effect, okay? And so that's that. Okay. All right. So okay. So I have one more thing I want to say about the quantum Hall effect, which is to make the point that it's kind of the same thing. You know, when I told you about the Su-Schrieffer-Heeger model, I told you that it's sort of a way of splitting the indivisible, splitting an electron in half. Okay? And in a way, the quantum Hall effect is kind of the same thing. Let me just show you the way it's the same. I mean, so if I start with a one-dimensional electrical conductor, so imagine then I have both left and right movers, you know, and I have to have both of them together. Okay? You can't take I can't have just one of them by themselves. Okay? But what I can do is split the right and left movers apart. And so let me just sort of tell you about this wire construction that one can do. So if I start off and I have a bunch of one-dimensional wires, and of course I could couple the right and left movers together on each wire, and that would give me a trivial insulator. But what I can do is I can couple the right movers on one wire to the left movers on the next wire. Okay? And so I hope you can see that this picture kind of looks like the same picture I drew you for the Su-Schrieffer-Heeger model. Okay, it really is kind of the same. And on the boundary between these two topological phases, one has these one-dimensional chiral edge states, okay, which get left behind. Okay, and so there's a sense in which it's all the same. Okay, we're doing the same thing. Okay, all right. So I'm a little bit behind, but I have 15 more minutes, so I'll get through some of this. Okay, and some of it will have to wait until tomorrow. In talking about the Chern number and the quantum, the TKNN invariant, that was all without any symmetry. Okay, and symmetry can give us a lot more. Okay, and in particular, I want to tell you about what happens when you have time reversal symmetry, and that can lead to a Z2 topological insulator. And then probably tomorrow I'll tell you. I'll get to the superconductivity. Okay, so let's talk about time reversal symmetry. Okay, so time reversal symmetry does two things in quantum mechanics. Okay, it complex conjugates the wave function. Okay, so that means that time reversal symmetry is a rather than being described by a unitary operator, it's described by an anti-unitary operator. That's something that involves complex conjugation. Okay, and it also flips the spin. Okay, if you have spin. Okay, so in general, this is the time reversal operator, and if you have time reversal symmetry, then that commutes with the Hamiltonian. Now, there's an important thing. Which is, if when I do time reversal on spin a half electrons, I have the up spins and the down spins. It gives me a complex conjugation. It flips the spin, and it does one more thing. It gives me this minus sign. Okay. Now this minus sign. So this tells you that if you do it twice, it squares to -1. Okay, and this -1. This -1 is actually it's the same -1 as the -1 you get when you rotate a spin by 2 pi. It really has the same underlying region. Okay, and it's a property whenever you have a half integer spin. Okay, so and what follows from this minus sign is a very powerful but simple-looking theorem called Kramer's theorem, which tells you that when you have spin a half system, every eigenstate is at least two-fold degenerate. Okay. Now, if you don't have a spin-orbit interaction, that's kind of a trivial statement. If you don't have spin-orbit interaction, then you're used to thinking you have every state, you can either put an upspin or a downspin in it, and those two states are the same energy. Okay? But when you have a spin-orbit interaction, you can't separately think about the states and the spins separately. So with the spin-orbit interaction, Kramer's theorem is a little bit deeper. Okay? And let me just, there's a very simple proof of Kramer's theorem, sort of proof by contradiction, which is, let's suppose you did have a degenerate eigenstate, chi, okay? So that commutes with the Hamiltonian. So that means that if I do time reversal, and it's non-degenerate, okay? So that means that if I do time reversal on it, I have to get the same state, okay? Because there's no, there's only one state there. So it's got to be some number times chi. So if I do it again, then what I'm going to get is it's anti-unitary, so I'm going to get C times C star times chi. Okay? And that's not consistent with theta squared being equal to -1. Okay? So the only way out of that is if there was also another state that it was degenerate with. Okay? So that theta on chi is some different state. It's not the same state. Okay? So what that tells us is that they all come in pairs. And so, for instance, if you have time reversal symmetry, you have to, and let's imagine you start with a one-dimensional wire. You have to have both up and down spin, left movers and right movers. Okay? So now, so what this poses is the question, well, can we, so I told you that, in effect, what the quantum Hall effect is about taking my one-dimensional electron gas and splitting it into chiral left movers and right movers. Okay? Now, of course, you can't do that with time reversal symmetry, right? Because the chiral mode by itself, if I do time reversal, is going to be going the other direction. Okay? So a chiral edge cannot respect time reversal symmetry. So in order to get a Chern insulator, you have to break time reversal. Okay? So, but what if you have time reversal? Then is there a way of splitting this? And so what you can do is you can imagine splitting it into helical edge states, which are edge states where the upspins are going one way and the downspins are going the other way. Okay? And so this, if I do time reversal, looks the same, right? Because under time reversal, the right movers turn into left movers, but the upspins turn into downspins. Okay, and so this stays the same. Okay, and so what that suggests is it should be possible to have some topological phase that has these helical edge states. Okay, and so that's what the quantum spin Hall effect is. And so these helical edge states, so what they'd be is you'd have states that cross from the valence band to the conduction band, but there has to be a state with positive group velocity and a state with negative group velocity. And so they necessarily then have to cross at 0. Okay? And so this crossing is something you might worry about, because usually you'd say that when you have states that cross, then any perturbation that you could add will make them anti-cross. Okay? But this is special, though, because of Kramer's theorem. Okay? If you have time reversal symmetry, then every state has a Kramer's partner at the same energy. Now, of course, if you're away from k equals 0, then this guy's partner is here at minus k. But at k equals 0, these two states that are crossing are their own Kramer's partners. Okay? And so there's no way you can get them to split. Okay? No perturbation that respects time reversal will lift this splitting. So there's a sense in which these helical edge states are protected by time reversal symmetry. Okay, and of course you have to, but in order to have them, you have to have the upspins and downspins are doing different things. So you have to have a spin-orbit interaction. And the simplest way of sort of getting at this is to imagine that you just have two copies of the quantum Hall effect. Okay, you have a quantum Hall effect with Chern number +1 for the upspins, and a quantum Hall effect with Chern number -1 for the downspins. And so then those systems, the up and down spins, would look like this. Okay, so that's the simplest way of sort of accomplishing that. Okay. Now, what I want to argue to you, though, is that what this simple picture would suggest is that there should be an integer Chern number, some spin Chern number that describes these topological phases. And so I want to argue that that's actually not the case. Okay. That actually there are only two possibilities. Either you have a trivial insulator or you have a topological insulator. And those are the only two cases. So when you have time reversal, the insulators in 2 dimensions are characterized by a Z2 topological invariant that only has 2 values. Okay? And so, to convince you of that, let's think about the spectrum at the edge. Okay? So I'm going to sort of draw this picture, but I'm only going to, since the left side is just a mirror image of the right side when you have time reversal symmetry, I'm only going to draw the right side between k equals 0 and pi. And so, so let's imagine we have an insulator. So we have a bulk conduction band and valence band separated by an energy gap. And it's always possible that there could be states that are localized at the edge inside the gap. There's no rule against that. That's always possible. Even in a completely trivial insulator, there could be mid-gap states, but they have to decay evanescently into the bulk when they're inside the gap. So, but the thing that we know is that at k equals 0, Kramer's theorem tells us that those states have to be twofold degenerate. Okay, so a state for the upspins and a state for the downspins. Okay. Now, when we move away from k equals 0, of course, if there's no spin-orbit interaction, then the up and down spin are always degenerate. But if there is a spin-orbit interaction, then the up and down spins can split because this guy's Kramer's partner is going to be at minus k. Okay? And it's going to be like that all the way until we get to the other end. When we're at k equals pi, then plus pi and minus pi are the same point there too. So these 2 points have to be Kramer's degenerate as well. Okay? And so once you see this picture that you have to have Kramer's degeneracies both at k equals 0 and at k equals pi, then you can immediately see why there are 2 and only 2 possible configurations. Okay? Because either the Kramer's pairs at 0 sort of match up with the Kramer's pairs at pi, sort of pairwise, okay, or they switch partners. Okay, those are the only 2 ways, because every other degeneracy in between is going to be split by something. Okay, you're never going to have degeneracies in the middle here because they're always going to be accidental. Okay, so these are distinguished by the fact that if I have a Fermi energy, then in this case it's always going to cut through an even number of bands between 0 and pi, whereas here it's going to cut through an odd number. Okay, and this even number could be equal to 0. Okay, so you could pull all these bands down. That would be perfectly okay, and you could have nothing at the Fermi energy. Okay, but in this case, if you tried to pull all the bands out, you can never get rid of this one. Okay, and so that's the difference between a trivial insulator and a topological insulator. Okay. And let's see. So what do I want to do next? So so again, this is the single particle picture. So let me try to give you some feeling for what about the many body spectrum? Okay. So how can I think about that? So is there really still a difference if I imagine there's some interactions now? So I have to think about the many body ground state. Is there still anything left to this topological distinction? And so let me try to argue to you that there's a picture that is sort of similar to Laughlin's argument that I showed you earlier. Okay, so let me remind you of the argument for Laughlin, which is that if you put your 2-dimensional quantum Hall state on a cylinder and you thread a quantum of magnetic flux, then that leads to a quantized change in the number of electrons at the end. Okay, and so in an insulator, if you thread a flux, nothing happens, right? In an insulator, since everything is localized, the electrons have no way of knowing that there's flux. You have to have an electron that goes all the way around the circumference to know about the flux. Okay, whereas in a quantum Hall state, you get this pumping of charge from one end to the other. Now, what happens in the quantum spin Hall effect? So the simplest case to think about is the case where you just have two copies of the quantum Hall effect for the up spins and the down spins. Okay, and so think about what happens. And now what I want to do is, rather than threading a whole flux, I want to thread half of a flux. I'll be done in just a minute. So I want to thread half of a flux. And if I do that, then what I know is that I'm going to thread half of an upspin electron to the right and half of a downspin electron to the left. Okay? So after that process, the spin on the right has increased by a half, by h bar over 2. And the spin on the left has decreased by h bar over 2. Okay? So it's as if I have changed on the right edge, I've changed from having an even number of electrons to an odd number of electrons. Okay? Or I've changed, the net spin on the edge has gone from being an integer to being an integer plus a half. The net spin has gone from, spin integer to spin half. Okay? And we know that spin half has Kramer's degeneracy. Okay? And so if you think about the spectrum, when you thread up a half of a flux quantum, what happens is that you have some finite sized spectrum at the end, but it's going to go from not being Kramer's degenerate to being Kramer's degenerate. Okay? So I have a unique ground state here. I have a twofold degenerate ground state here. Okay? And in a trivial insulator, that wouldn't happen. Okay? But this is what happens in a topological insulator. Okay. So it's 11 o'clock. I think I'm going to skip this. I think maybe I'll finish for today, and then I'll pick up a little bit of this tomorrow, but spend most of the time talking about superconductivity. So does that sound good? Okay. Thank you.